Hello everybody, we're going to talk about capacitors. We're going to finish talking about capacitors. So let's start with the definition of capacitance. And capacitance is kappa epsilon naught A over D. On the AP formula sheet, what you're going to see is epsilon naught A over D. And kappa is the material constant for capacitance. So it is a material value for insulation, and it's called the dielectric constant. And a dielectric, it might help you to think dielectric, is just a fancy name for an insulator. So a dielectric is a fancy word for insulator. So a capacitor is made up of two parallel plates. They're conductors. This is a conductor, and this is a conductor. And so they're called parallel plate conductors because you've got two conductors, and these will be attached to wires on either side. And then in the middle there is typically an insulator. This piece is the insulator, and it is called the dielectric. The most common insulator is actually air. Is air. And you probably know that air is a pretty good insulator, because if you think about how much current, how many charges have to build up to be able to store electricity, and then let it go in a lightning bolt, you'll realize that air is a pretty good insulator, because otherwise the electricity would be constantly moving from the sky to the ground, and it would sort of be dangerous everywhere. But since air is a really good insulator, it takes something like 9 billion charges to shock yourself on a light switch or to shock a friend. It takes nearly 1 million volts of energy to build up enough to have a lightning bolt from the sky. So air is actually a really, really good insulator. And usually the dielectric is air, which means the K value, that kappa that we were just talking about, is 1. But different materials have different amounts of insulation. So for example, if you were to put plastic or glass in between the two plates, you would have a different behavior. You'd have more capacitance, because that's a stronger insulator, if you will. Now, when we talk about this, the way these work is you have, in a circuit, you have positive charges be coming down, because we always treat it like it's the positive charges that come down, and we're piling on. So this is from the battery. It's from the positive terminal of the battery, or the positive side of the battery, and the electricity comes down, which we assume are the positive charges, even though we know it's the negative charges. And what happens on the bottom is you have, let's get this different color here, you have some negatives in this piece as well as positives, because normal materials have both positive and negative charges. They have them in about equal amounts, and so what we've got is our conductor starts neutral, but as the battery starts to push charges onto the top plate, the charges on the bottom plate, the little positive charges, feel the field that goes through the insulator, because the field goes through the insulator but no charges do. No charges go through the insulator. So really don't mess that one up. Go through just the field. You can just feel the field. So the field goes from positives to negatives, and these positives down here, some of them that are free to leave, start to run away. So then we get a positive charge flow back to the battery. So this is how a capacitor charges up. Now, when we talk about a capacitor charging up, we don't ever get to full charge. So what you're doing, just to give you an idea, if we have Q, which is charge, over T, which is time, our charge will build up really quickly, and then it'll flatten out to whatever the max is. I use the word max here. The maximum amount of charge will be sort of like an asymptote, so this thing will belly up to it. Sorry, that's not very straight, so let's try that again. Let's get this a little, there we go, that's a little bit better. And so the capacitance will go here. So we consider there's a moment in here where time equals resistance times capacitance, and we call that the time constant. And that's the moment at which, probably a little bit further over, it's the moment at which you go from gaining really rapidly to gaining really slowly. So the time constant is when we call our capacitor charged, because you can see that it's an asymptotic curve, and so as it approaches that asymptote, it's only gaining tiny, tiny, tiny bits of charge over and over. So we generally consider it charged at about 63%. So when it's about 63% charged, we call that a charged capacitor. And what happens when we get to charged is, when we get to charged, now we have a, I'm going to take out the words insulator here real quick. We have a very strong field, and the electricity stops coming on, so the electricity also stops going off. So these charges that have left have left. And so now we have a positive charge on the top plate, positive Q on the top. We have negative Q on the bottom. And there is no flow anymore because there's no place to put any more charges. So you can kind of think of a capacitor like a bucket of charge. So it's a bucket of charge that fills up. And so as you pour water in, like if this was a water bucket, the water would start rising and rising and rising. And at some point you have to turn the water off because you can't go above the maximum capacitance. Well, what happens in a capacitor is very similar to that, with one small difference, and it's the significant difference in this case. As we start piling up charges in here, charge flow keeps coming in, charges keep flowing in, but at some point there is actually no room for any more charges, and because of the nature of the field on this top plate also, we have an electric field that pushes this way, and on the bottom we have an electric field pushes that way, and of course on the sides and everything. So the electric field points away from the positive, so this thing gets more and more charged, means this field gets stronger and stronger and stronger, and then positives don't want to come or can't come because they can't push against that flow, they can't move against the field. And so it sort of generates its own back current, it generates a back EMF, back voltage, to prevent any charges from coming onto it. Okay, so now, how do they behave in circuits? Well, let's get us a circuit up here and look what happens. So I'm going to look at the one that you see on the top right over here. So we have a battery, and this one is 10 volts, and we have a resistor. Then we have another battery over here that's 6 volts. We have a switch. Have another resistor, another resistor. Oh, wait, I can't do this one. Sorry, that one doesn't have a capacitor in it. That's what you do with different batteries. Let's do the one that's got the 10 volts. So it looks like this. AP sometimes draws your batteries in kind of interesting ways. It looks like a stack of batteries instead of just one. So what we have here, this is called a Wheatstone bridge. Those of you that do electricity might know what that means, and those of you that don't, and it's really, really okay. You don't have to know what a Wheatstone bridge is. What you do have to know is how this puppy acts when you add a capacitor to it. So we've got two paths, resistor number 1, resistor number 2. That's a terrible resistor, I apologize. But you've got a much nicer picture on the right. so that you can follow along. Alright, so here's our capacitor. So when we first turn this on, this side acts like a 20 ohm resistor, this acts like a 10 ohm resistor, and if this is uncharged, if you start with this uncharged, it acts like a bare wire, like a plain wire. So the resistance on this path is 10 and the resistance on this path is 20. So guess what happens to the current? Well, the current starts coming in and a little bit of it goes there, but a lot of it is going to break and go in this direction. So we're going to get a lot more flow here than we have here. And as that flow comes down through the resistor, we start piling up charges on the capacitor, and we start running charges off the capacitor while this one is just continuing to go through and back around. But as the capacitor becomes charged, here's what happens. Sometime later, and the way they say this in AP is they say something like, a long time later, when the circuit has reached its steady state, so we use words like long time later, steady state. These words mean capacitor is charged. So what they're telling you is you now have a charged capacitor. So what happens is this now, because my capacitor is full, it is creating an electric field that pushes back. So we have a electric field that pushes that way and pushes this way. On the other side of our loop, we've still got those two resistors, but what we've got in terms of the path now is this path will not take any charge because the capacitor is charged. There's nowhere to put charges, so this voltage equals the battery's voltage. So like if this is 10 volts, the voltage over here on the capacitor is now 10 volts. You don't lose anything on the resistor because there's no flow, there's no current, no current. Capacitor equals battery, everything's the same. And your circuit becomes just this. The only flow is now going this way. So once you have a capacitor that's charged, that branch or the part of the circuit that it's on is now equal to 0. So a couple of things to keep in mind. Number one, here's our quick hitter review for capacitance. Number one, capacitors in series add to find total capacitance as reciprocals. Which is exactly the opposite of what a resistor does. So if you have series circuit, the total capacitance is equal to 1 over capacitor 1 plus 1 over capacitor 2 plus 1 over 3 and so forth. It also means that once, number 2, once the small, come on man, once the smallest capacitor is full, the whole circuit stops. So it doesn't matter where the smallest capacitor is, since all the objects are in. So if we had, here's our battery, we had a resistor here, we have a capacitor here, we have a resistor here, we have a capacitor here. If this is a 10 farad capacitor and this is a 20 farad capacitor, what's going to happen is the flow is going like so. It's series, so everybody gets used. But this guy will fill up first. He's the smallest bucket. So when he becomes full, he doesn't allow any current in, he doesn't allow any current out, which means this one will only be partially full. How full will it be? It will be 10 farads worth. Okay? So the charge on each capacitor is the same. So let me say why that happens. Remember, positive charge is coming out. I'm going to erase this for just a second now. I've got some extra pieces. Take the word full out. Take that line out. Take this line out. So what happens is the positive charges go here. They start to pile up. But every single charge that comes onto this plate runs a charge off the other side, and that makes this one become positively charged. But at some point, this one, the 10 farad, the little one, is full. And when it's full, it can't take any more. And if it can't take any more, no more runoff. So even though the second one is capable of holding more charge, it doesn't have any charge to go to it. Now a lot of people think that it would be okay if we could fix it by doing this. Put the 20 here. Still do your resistor down here, put the 10 down here. But realize it's the same problem. So as the positive charges come over here and start to fill this one up, every charge on this plate is matched by a charge on that plate. As this charge comes in, one runs off. At some point, this side becomes full. When this becomes full, it will not allow any charges to come in. And if it doesn't allow any charges to come in, the second capacitor, even though it's not full, will not allow any charges to come in on that side. Okay? So once a capacitor is charged, you do not get the full amount of, you don't get the full capacitance on the bigger ones. The littlest one gets full, and then all the other ones have to stop. But what that means is because each charge is matched on every plate, the plates, all the plates will have the same amount of charge. Okay, and that's what I mean by this. All these plates. So if this was 20 charges, 20Q, this would be negative 20Q, this one would be 20Q, this would be negative 20Q. So they would all have the same charge, but they'd have different voltages because they're different sized capacitors. Okay? Now, another page. That's what happens in series. So what happens in parallel? So capacitors in parallel add directly. So C total is C1 plus C2 plus C3, ... So what you may notice is resistors in parallel add inversely. Resistors in series add directly. But the crazy part about that is the capacitors do the exact opposite. So resistors do one thing, capacitors do the exact opposite. So why does this happen? So what we're really saying is now in parallel we have multiple buckets. So here's let's go over here and do another battery like AP likes to show them. And let's show capacitor, capacitor, and just for funsies we'll put a resistor down here. So let's make this a 10 farad and a 20 farad. So the second bucket is bigger. So what happens initially? Charges flow here and there's a junction, so some charge goes here, some charge goes here, and almost none goes to resistor to start with. Almost none. Not none, but almost none. And so as time passes, we've got these cute little guys are filling up. And at some point, what happens is this one becomes full. And he quits taking charges. So he stops taking charges. So no more current goes there. Which means now, more current starts to go to the resistor, and we're still filling up to 20. So now we're filling these two. And at some point, this one becomes full. Sometime later, right, because it's bigger, this one is now full. Now my circuit turns into just one big loop with the resistor, and the two capacitors are full. So that would be how that behaves. So you don't have to have the same one person stops everybody. Since they're on different loops, each of them can get all their voltage possible. So what happens here? Well, the voltage on this one will equal the voltage of the battery, and the voltage on this one will equal the voltage on the battery, but we will have different amounts of charges because they're different size buckets. They are different size capacitors. They're different size buckets. One can take twice as much water as the other one. Okay? And once they're filled up, they don't allow any more current to flow. So the question becomes, how do you discharge them? Well, when you discharge them, so in the last piece, discharging a capacitor is really rebalancing the plates. So you have a positive charge up here, you have a negative charge down here, and what we do is we make a connection, usually with a switch, and the switch will connect the positive to the negative, and so all these charges, negatives will run up here, positives will run down there, and they will rebalance so that the two plates are neutral again. Now, when you discharge a capacitor, the current is going to, so here was your max Q, so here's my Q. So we start with the maximum, and it's going to drop off really fast, and then it's going to trickle out. Much like if you took a bucket full of water. Take a bucket full of water and you flip it upside down. Not all the water comes out immediately. Most of the water comes out immediately, so it's like a big flood. But then it'll drip. Little drips will from the top to the bottom and down the sides. So when we say discharged, we mean it's rebalanced, even though it takes a long time for that to actually happen. We're kind of really only thinking about the first dump as our discharge. So where a battery is more like a water faucet, a capacitor is more like a bucket of water that after you win the big game, you flip the bucket of water over your coach's head. Most of the water comes out at once. So currents in water faucets are nice and smooth pieces. In a capacitor, it's a dump and wait, dump and wait, dump and wait. Okay, so that's how capacitors work. Now let's look at a couple of problems on this. Get me a new sheet of paper. So let's look at some, let's start with some multiple choice. And we'll look at this one right here, number 53. I'm going to minimize that just a little bit. So number 53. And once again, if you'd like to wait and see if you know how to figure it out, you can always pause the video and then you can figure it out. So here's what we have. Because I'm a person that likes to draw the pictures, even if they have the picture for me, I'm going to do this. So there's one of my loops, and here's my second loop. Oops. Let me fix that. There's a capacitor in there. And the reason the capacitor is shown as a gap in the middle with no wire is because there's a gap in the middle with no wire. If you ever get charges to jump from one plate to the other, you have just burned out your capacitor. We call that breakdown voltage. I may talk about that here in just a second. So this one is 3 times 10 to the negative 6 farads. This is 200 ohms. This is 300 ohms. And this is 100 ohms. So they ask you the current through the 6 ohm resistor. Excuse me. The current in the circuit diagram, this is number 54. In the circuit diagrammed above, the 3 microfarad capacitor is fully charged and the amount of charge it has is 3 microfarads, and it has 18 times 10 to the negative 6 coulombs of charge. So this is farads, this is capacitor size, capacitance, and this is charge. Okay, and they tell me it's fully charged. What is the value of the power supply voltage V? Okay, well, let's see. What we have here is it's fully charged. So no current will go down this piece at all. Okay, no current goes down that piece at all. It's done, it's charged. So the question is, what is the voltage? Well, if I know what's happening on the resistor and the capacitor, then I'm okay. But if I have no flow, the resistor uses no energy, and it uses no energy because now there's no current through it. Okay, so the voltage on the capacitor has to equal the voltage on the battery, and this is because a capacitor stores energy. Okay, so if we can figure out what the voltage on the capacitor is, we can also figure out what the voltage on the battery is. So here's what I'm going to do. There's another formula, and this is the other one we need to know, and it's capacitance. We already had the kappa epsilon naught A over D, but in a circuit, so this is sort of just the definition. In a circuit, capacitance equals charge per volt. So that how many charges will I hold? At some voltage. So a voltage tells you how much energy you get per charge. So capacitance only hold a certain amount of energy. So let's, for example, say if we had 100, our capacitor could hold 100 joules of energy. Well, that means that it could hold 4 charges if the voltage was 25, because 4 charges, each carrying 25 volts of energy, would go up to 100. So if each charge gets 25 volts, you can only hold 4 of them on my 100 volt capacitor. But if my voltage was 10, if I only give each one of the charges 10 joules of energy, now I can hold 10 charges. And if you gave each one of the charges 1 volt of energy, I could hold 100 of them. So capacitors store energy. And if you have a lot of energy, you're going to have a few charges. You don't need many charges to make up the total for the energy. But if you have a little amount of voltage, a small amount of energy, then the capacitor is going to have a lot more charges on it, because each charge has to add to my total overall energy amount. So that's how we're going to work this problem in number 54. So this is actually number 54, and I apologize for that. Number 54. And on number 54, we know that capacitance equals Q over V, delta V, and we have those values. So this is 18 times 10 to the negative 6 equals 3 times, whoops, I got my numbers backwards. This one is 3, this one is 18. Times 10 to the negative 6 over voltage. So voltage equals 18 times 10 to the negative 6 over 3 times 10 to the negative 6. So we get 6 volts. And so that would be our answer to number 54. It's letter B. Okay, let's do another one. Not finding one. Okay. Let's look at number 71, and feel free to pause on this. For the configuration of capacitors shown, both switches are closed simultaneously. After equilibrium is established, what is the charge on the top plate of the 5 microfarad capacitor? So here's what we've got. We've got plus 100 microcoulombs minus 100 microcoulombs, and we're going to connect it directly to a minus 50 microcoulombs. Sorry, that's terrible. And a plus 50 microcoulombs, and we're connecting them up like so. And they say once it reaches equilibrium. What does equilibrium mean here? Well, let's see. The trick is going to be this one has positive, this one has negative. So we have a net of 100 minus 50 is 50 microcoulombs. And to be equal, we're going to have to divide that 2. So this one is going to turn into 25 microcoulombs, and this one is going to turn into positive 25 microcoulombs, which means these two at the bottom are going to do the same thing with negative for the opposite signs. So over here, sorry, this is your negative on top, and this is your positive on this one, because you always have to have a positive connected to a negative. So our net was 100 minus 50 is 25 extra positives, which will then distribute to be equal on both sides. So they each go to equilibrium, meaning we're getting as close to net charge of 0 as we can. We can't get very close, we get to 25, but that's the best we can do. So they ask, what's the charge on the top plate of the 5? So what is the charge here? 25 microcoulombs. That's how it works. 25 microcoulombs would be the net charge. Okay, so let's do one. Let's do one number 76. And yes, I'm doing a few more of these because this is a teaching, not so much. It is a review, but it's also a teaching of these characteristics. So I'm going to do one more like this, and then I'm going to go to one that's a free response. So for the RC circuit shown, resistance is 10 ohms, capacitance is 5 farads, and battery has a voltage of 12 volts. The capacitor is initially uncharged, so it's an empty bucket right now. And then we're going to close that switch. Sometime later, there's our keywords, sometime later, now the current in the circuit is 0.50 amps. Okay, so is our capacitor charged? Not completely charged capacitor. It's not completely charged because if it was completely charged, there would be no current in the circuit at all. Once that capacitor got full, there would be no flow. No charges coming in, no charges going out. So we know that they ask us now, at some point later, when we're not completely charged, what is the voltage across the capacitor? So they want to know, I'm here, I've got a current of 0.50 amps. What is the voltage here? Well, this is an easy problem if you'll remember that this is still charging. So if it's still charging, this is kind of acting like a wire with some voltage. But then we've got this piece. And voltage on the resistor is current on the resistor times resistance of the resistor. And we know those in this case. So the voltage used on the resistor is 0.5 amps times 10 ohms is 5 volts. So the resistor is using 5 volts. So by the loop rule, to pull that one again, the loop rule says if you go in a circle, sum of the voltage is in a loop equals 0. So we have 12, we gain 12, we lose something on the capacitor. We lose something on the capacitor, and then, hang on just a second, folks. Okay, so let's go back down to where we were. Sorry, I had somebody come in. So 12 minus the capacitance, and then, so this would be the voltage on the capacitor, and then the voltage on the resistor is 5, would have to equal 0. So 12 minus 5 minus V cap plus 7 equals 0. So the voltage on the capacitor must equal 7 volts. It must take up the rest of the voltage when you go around the loop. So that's another way they might ask about capacitance. And occasionally you'll get one where you just have a bunch of capacitors and you're supposed to add them together, so you have to know they're series or not. I'm going to go down here to where we have a capacitor. Yes, 1988 B3. This is the last one I'm going to work here. So 1988 B3. And if you want to pause at each section, feel free to. So I'm going to redraw the circuit to start with. So I've got, let me erase this down here so I can put it down here and I can work on one part and I can talk about the circuit on the other part. So I'm going to erase this part. And of course it doesn't go away because you can always rewind the video. Cool stuff, right? Okay. So there we go. So here we go. Here's my circuit. So this is a 72 volt battery, 6 ohms, and just bear with me while I redraw this. There's a reason I redraw everything, especially when I'm teaching, because I want to be able to mark all over crap, and you can see where my reasoning's coming from. 10 ohms, 2 ohms, switch, capacitor. Yes, I know my circuit's getting a little crookedy. 3 microfarads. Okay, so switch 1 is open. Capacitor's not connected. Under these conditions, determine the current in the battery, the current at the 10 ohm resistor, and the voltage at the 10 ohm resistor. Okay, so how are we going to do the current at the battery? Well, to do the voltage at the battery equals the current at the battery times the resistance at the battery. But the resistance at the battery is the total resistance for the circuit. So what I'm going to do is I'm going to see that if I come out, I'm going to start tracing. That's a series one, so that's going to be just add directly. But right here I get a split. And if I go down this path has 12 ohms of resistance. And if I come down this path, this has 4 ohms of resistance, and these are in parallel. So the first part I'm going to do is resistors in parallel is equal to 1 over 4 plus 1 over 12. And yes, AP wants to see all of these steps. So this will be 3/12 plus 1/12 is 4/12. So 1 over R parallel equals 4/12. So R parallel equals 12 over 4, or 3 ohms. Okay? So that's the first piece they're going to want to see in part A. The second piece they're going to want to see is R in series is R1 plus R2. And in our case, R in series is going to be 6 plus 3. So 9 ohms total. Now we're ready to answer the question. Voltage at the battery equals current at the battery, resistance at the battery. So 72 equals I times 9. So I is 8 amps. For those of you that are curious, it only takes about 1 milliamp. It can take as little as 1 milliamp to kill you. 10 milliamps is usually the one that they say is the cutoff for death, but 10 milliamps is nowhere near this. If you grabbed a hold of this circuit, it'd drop you like a rock. Okay, so there's part A. So once again, what did I have to do? In essence, and I'm going to walk this back a little bit with you. In essence, this circuit acts like you have a battery, a 6 ohm, and over here you have a 9. So it acts like there's a 6 and a 3. The parallel piece acts like a 3 ohm resistor. So those two pieces together are what adds up to that. And so when we do our total resistance, it's a series at the end because you have battery, 6 ohm resistor, and then into the parallel piece only gives you 3 ohms of resistance. Okay, so now, that was my first bit that I was going to do. So now, let's take these markings off, and let's see what the rest of the question is going to ask me. So the next part says, the current in the 10 ohm resistor. So now it wants to know what the, we want to know that coming in here is 8 amps of current. Coming out here is 8 amps of current. They want to know what happens here and here. What happens along these two paths? Well, this is where it's pretty cool. What is the ratio of resistance? 12 ohms to 4 ohms. So that is a 3:1 ratio on resistance, which means we have a 1:3 ratio on current. What do I mean by that? Well, let's go back. V equals IR. So if R goes up, I goes down. If our ratio of resistance is the second loop, this one over here, has times 3 the resistance, so this one gets 3 times the current because it's the path of least resistance. So all we have to do now is do this. 3:1 ratio. So how's that going to work? Well, how much current comes in? 8. So I need to break 8 into a 1:3 ratio. How are we going to do that? Well, let's see. It's a ratio, right? Let's erase all this. We can take that off now. We can go, oh, okay, so, right, 8 over 8 minus x equals 1:3. Because the two currents have to add up to 8 altogether. So we get this. 24 equals 8 minus x. So x must be 16. Hang on just a second. That's not going to be the, I don't think that's the easiest way for you to see this. Let me back this up. Let me do it like this. It's a 1:3 ratio. So we divide 8 into 4 pieces. Maybe this will be more understandable for you guys. Divide 8 into 4 pieces. So that would be 2 amps. The little one is going to get 2 amps of current. The big one is going to get 6 amps of current. So that the ratio of current is 3:1. The little one has 4 ohms of resistance, so it gets 3 times the current. The big one has 3 times the resistance, so it gets 1 times on the current. So we divided it into 4 pieces, and then we split them up. So 2 went on top, that's 1 chunk of current, and 3 goes on bottom, the other chunk of current. That's probably the quickest way to do that. Okay. So I'll let you stop and think about that for a second. I'll take all these pieces out. Actually, I didn't want to take that last one out. Just this one. Okay, so now what's the last part? So what's the current in the 10 ohm? The current in the 10 ohm for part B. Here's the math I would show. Resistance is 1, 2, 3. Here's how I'm going to show that. Resistance of path 2 to resistance of path 1. 1 to 2. Let's get this right. 1 to 2 comes from 4 over 12. Okay? So current of 1 to 2 would have to be, flip that over, 3 to 1, which would be 24, or excuse me, 6 amps over 2 amps. And you could work it as we have 8 total, so 3 over 1 is going to be how much ever comes in up here, x, to 8 minus x. And if you do it like this, that's the other way to work the problem. You get x equals 24 minus 3x, so 4x equals 24, so x equals 6. So you'll notice that the X one goes with the high resistance, goes with low voltage or low current. Low resistance goes with high current. Okay. I think I've kind of beat the dead horse on that piece. But you guys are patient. We're alright. Alright. Now, last but not least, the potential difference across the last one, I'm going to erase again up here. I think we got this. I'm going to kind of give myself space to work. Okay, so here's my space to work. So now I know that this part has 6 amps. This part has 2 amps. So if I want to know what's happening at this circuit, V on the 10 equals I on the 10, R on the 10. So V on the 10 equals I, which is 2 times 10, so 20 volts. So that was part C. C's really easy. Now, all this while, this guy was starting to fill up. Okay? On part B, sorry, I skipped the reading of the next part. So now my circuit's going to change. So all this work that I did before is now going to go. So we're going to go to case 2. Case 2 says this. We're going to close this thing. So now where does almost all the current go initially? We're all going to go down here, because that's going to act like a bare wire to start with. So if I have a choice of no resistance and resistance, I always pick no resistance. So the capacitor shorts the first 2 paths at the first moment. But we're not looking at the first moment. When are we looking at it? We're looking at it, once again, it's that long time. Capacitor, what they're saying to you is the capacitor is now charged. Long time, currents are constant. Those things tell me that the capacitor is now charged. If the capacitor is now charged, the voltage across it will be 72 volts. Super easy to do. You do that as a loop. Battery to capacitor to battery. It's only one device on that loop, so it has to be 72 volts. That part's super easy. Leave that alone now. So it's charged. What is the charge on the capacitor? Capacitance equals Q over V. So this is 3 times 10 to the negative 6th. Let me put it up here where I was going to write it. C equals Q over delta V. So Q equals C delta V, which is 3 times 10 to the negative 6th times 72. So the amount of charge is 3 times 72 is 216 times 10 to the negative 6. So that would be, move 2 over, 2.16 times 10 to the negative 4th coulombs. I write coulombs because this is a C and this is a capital C, and I don't want my charge and my capacitance to get confused. That would be bad. And then last but not least, the last thing we need to know, what is the energy stored on a capacitor? Straight formula. So energy is 1/2 QV. It's also 1/2 CV squared. It's also Q over 2C. The easiest way to do it here is this one. So 1/2 of 216 times 10 to the negative 6th times voltage of 72. Now I need a calculator. So come down here. Where's my calculator? Come here, little friend. 216 E negative 6 times 72 times 0.5. So it is 0.0078 joules. And there we go. So I'll do another one of these. I'll do a review of capacitance later, but this is your lecture for Thursday, April 15th. And you need to practice some of these AP problems. It's really important that you do so. All right, I'll catch you on the next lecture. Thanks.